OCamlCC.
So thank you. As you just said, my name is Benoit Vaugon, and my talk today will present collaborative work with my PhD advisor Michel Moni about raising low-level bytecode to high-level C. Precisely what we want to do. We want to translate an OCaml bytecode executable file into a C source file, which can be compiled by a C compiler into native code. So our constraint, or I should say our choice, is to use the standard OCaml runtime. So it implies to use the standard garbage collector and the standard data representation as in OCaml. So we have the same semantic as a standard OCaml program. Our main goal is to obtain the same performance, to obtain native code performances with bytecode portability. So a positive side effect of our toolchain is that we extend strictly the OCaml bytecode compilation chain. What I mean by that? I mean, if you want to compile an OCaml program written in some ML files, you start to compile it in bytecode executable as usually, and you can use our OCamlCC compiler to translate this executable file into a C source file, one C source file. This file includes the standard OCaml runtime slightly modified, and you can compile it with a C compiler like the GCC to obtain a native executable file. So remarks that in this single row is where all our work is. So how can we generate C from bytecode? It's a translation in 3 steps, the first and last are not stop rising. The second step starts with a kind of decompilation. We start to translate each lambda abstraction, each OCaml function, into one C function. So the goal is to cut the C file, the C code, into not exactly human readable code, but C compiler readable code. So we perform lots of optimizations based on the whole program. We have an analysis, strong analysis based on a whole program. So precisely, we do not optimize directly the code. We just generate optimizable C code. So for an example, we do not perform inlining. We left this to the C compiler. So most of our optimizations or analysis are based on abstract interpretation, but not all of them. Our main optimization are the following. So we perform a kind of code pointers forwarding. So I mean to transfer code pointers as far as possible in the code. The main goal of that is to permit to the C compiler to perform inlining, because if you left code pointers into closure, which are in the C heap, pointed by lots of global pointers, global variable, the C compiler cannot perform constant folding and cannot inline function. So we forward code pointers onto some other constants. These two optimizations are just consequences of the first, because when we remove code pointers, we can remove some closures creation or some parts of the environments. The last optimization is a strong optimization. It consists in moving OCaml value from the bytecode stack to the C stack. So let's get a bit technical at this slight point. I mean by moving value from OCaml bytecode stack to C stack to transform OCaml stack access into indirect stack access into C local variable access. So usually, like in the OCaml interpreter, OCaml run, the OCaml stack is simulated by a C array. So access are very long, and the C compiler cannot optimize the code. So we want to transform this access into C local variable access. So warning, you cannot perform this optimization, always perform this optimization, because you have a garbage collector, and the garbage collector moves data. So you must first to register live blocks to the garbage collector, and when you have, it is not sufficient. In practice, you must register all data memory word which contains an address in the heap. So to perform this optimization, we use heuristics based on the disjunction of these three conditions. We tell that a stack cell can be safely extracted from the stack if it is never read as a pointer, as a heap pointer. So to be read as a heap pointer, I mean to be dereferenced, or to be used as an unknown ways. So like passing to an unknown function of this kind of thing. The second condition is to be never written as a heap pointer, or if no garbage collection may occur during its lifetime. So it is a positive side effect of this algorithm. We can observe that sometimes some heap pointers are safely extracted from the stack. You have a simple example when, for example, a function never never perform allocation, and no GC can be run during its execution. So you can extract safely all the function frame, the stack frame, from the bytecode heap. We have more complex examples when you manipulate a pointer, but you never dereference it. You just check if it is a pointer or not. And in this case, you can extract it from the heap. The effectiveness of this algorithm is good because, for an example, on the OCamlCC, when you bootstrap OCamlCC, to bootstrap OCamlCC, I mean to take the OCamlCC compiler compiled in bytecode and to compile it with OCamlCC in native code. It is a huge program, near than 1 megabyte. So we extract near than 85% of stack cells on this code. So it is well known that if you compile a functional language into C, you have some common problems, some common difficulties to transform structures which is not present in C or which is not correctly compiled by C compilers. So I will present the four main difficulties. So how we translate exceptions. Exceptions, we try two ways to translate exceptions. The first one is to generate a set jump, long jump code, as in the OCaml runtime. And the second one is to generate C++ and to use a try-catch mechanism, a try-catch C++ mechanism. So OCamlCC takes an option to choose the mechanism you want to use. You will see that the second option is not always, but almost too slow than the first. I will explain that later. The second problem is management of takeovers. So when you write a program in OCaml, you know and you want to use the fact that takeovers are correctly implemented by OCaml compilers, OCaml standard compilers. So when you write a program in C, you know that C compilers do not implement correctly tables. And this is due to two main facts. So you have lots of other reasons, lots of other cases in which C compilers do not implement correctly tables. But the first main reason is when you have a set jump call in the same function scope. If you have a set jump call in a function, GCC, for an example, never implements tables in the same function. So the second reason is due to the C compiler, the C calling convention, which is very different to the OCaml calling convention. And for an example, with GCC, when the callee receives more arguments than the caller, the tables are not correctly implemented. So we have two implementations. The first one is not beautiful, precisely the first is very horrible. So it is an architecture on GCC-specific solution in which we generate assembly code to perform tables. But we want to be portable, so we have another pure C solution. For the set jump problem, just in this case, we subscope set jump calls in a local function, in another function, precisely. And for the problem of number of arguments, we use global variables sometimes to pass some arguments. So the third problem is signal handling. When you call a signal handler, the memory must be in a consistency state. So the solution is the same as the standard OCaml solution. It's to call a global flag. So the problem is when call this flag. If you do it too much, you are too slow, and if you do not hit enough, you lose in reactivity. So it is left as an option for a user. The last problem is when we generate a C file, we generate just one C file. So it is a huge C file. For example, when you bootstrap OCamlCC, you obtain a C file with all its dependencies and includes which contains more than 1 million instructions. But in practice, GCC or some other compilers compile it in near than 1 minute, so on a standard computer. So it is not a big problem. But if in the future it becomes a problem, we can perform separate compilation to solve it. So what about time performances? On this graph, we compare 4 ways to compile and execute an OCaml program. Examples are taken from the OCaml test suite. And warning, we do not compare time execution, but we compare speed ratio. Our starting point is the OCamlCC compiler and OCaml interpreter in green. We compare us with OCamlJIT2 and with OCamlOpt. Our compiler OCamlCC is in red, and we can see that we are always better than OCamlC and OCamlJIT2, and almost slower than OCamlOpt. Just in some case, we are very near OCamlOpt. When you bootstrap OCamlCC compiler and you recompile a standard library, we are just near OCamlOpt, and sometimes we are very faster than OCamlOpt. On some micro benchmarks, you compile Fibonacci or the tag function. So tag GCC, because we obtain 10 or 14 factor with OCamlCC. On the second graph, we compare speed ratio on the same examples. So just when we change the C compiler and the exception mechanism, in red you have when we use GCC, in green when we use G++ with exceptions, and in blue when we use C-long, the LLVM C compiler. So we can see that GCC is almost better than others, but not always. So, conclusion. Our goal was to implement a compiler from bytecode, from OCaml bytecode executable to C code. We obtain our goal of portability, because we have the same portability of the bytecode interpreter. We support 3 C compilers. We just test 3 C compilers actually, GCC, G++, and C-long. Our code is distributed on this link, so you can try it and report bug. So actually it seems to work, and we have good performances. In future work, we want to perform some other optimizations like optimization actually performed by OCamlOpt or OCamlG2, like people optimizations and floating point arithmetics or this kind of thing. And we want to try other C compilers like the Intel C compilers. All of that. Thank you.